We have another always, sometimes, never question. So 3.3.1.1, let L sub A be a linear transformation from Rn to Rm, and define L sub B to be a function from Rn to Rm by L sub B of x is equal to beta times L sub A of x, where x is a vector from Rn and beta is a scalar. Then L sub B is a linear transformation. We want to decide whether this is always, sometimes, or never true. I believe it's most likely always true, so I'm going to try to prove it. If I can't prove it, then it might suggest that something is wrong. It might also suggest a counterexample that I can find for the problem. So I'll look more deeply at whether it's sometimes, always, or never true by trying to prove that it's always true. So what do I need to do here? If I want to show that L sub B of x is a linear transformation, I need to show two things. I need to show that L sub B of x is, actually, I need to show that L sub B of alpha times x is alpha times L sub B of x for all scalars alpha and vectors x in Rn. What else do I need to show? I need to show that L sub B of x plus y is L sub B of x plus L sub B of y for all vectors x and y in Rn, because these two conditions must hold for a linear transformation. So let's see if I can do that. I'm going to start with L sub B of alpha times x. Now, by definition, this is actually equal to beta times L sub A of alpha times x. But this is actually the same as beta times, this is actually alpha times L sub A of x, since L sub A is a linear transformation. I'm just going to use LT for linear transformation here. Beta is just a real number, and so is alpha. So we actually have beta times alpha times this vector. Well, we know that scalar multiplication, or the multiplication of two real numbers together, is commutative. So this, by commutativity of multiplication of real numbers, is the same as alpha times beta times L sub A of x. I could have used parentheses here, but I don't have to because of the idea of commutativity. And so this is equivalent to this, but beta times L sub A of x, that's just what we called L sub B of x by definition. I'm done. It is true that L sub B of alpha times x is alpha times L sub B of x. That wasn't so hard. Let's try the next part. We would need to show that for all vectors x and y, L sub B of x plus y is L sub B of x plus L sub B of y. Let's do the same thing and start with the left-hand side, L sub B of x plus y. Well, by definition, what is that? It's just beta times L sub A of x plus y. Well, L sub A is a linear transformation, so this is equal to beta times L sub A of x plus L sub A of y. Since A is a linear transformation, it has to satisfy this condition that L sub A of x plus y is L sub A of x plus L sub A of y for all the vectors A and y, x and y. So this is just true because L sub A is a linear transformation. Now what do I have? I have beta, which is a real number, a scalar, times L sub A of x and L sub A of y are both vectors. But I know that scalar multiplication distributes over vector addition. We proved that back in week 1. So this is equivalent to beta times L sub A of x plus beta times L sub A of y if I wanted to put parentheses around these, I could. I didn't have to. And this is because scalar multiplication distributes over vector addition. So now what do I have? This piece is just L sub B of x by definition, and this piece is L sub B of y by definition. So actually I'm done because I've just proven for all vectors x and y, L sub B of x plus y is L sub B of x plus L sub B of y. Okay, that means that L sub B is a linear transformation. We're done. So it's always the case that if L sub A is a linear transformation and L sub B is just a scalar times a linear transformation, then L sub B itself is a linear transformation. So in other words, in English, if you take a linear transformation and you multiply it by a scalar, then the result is another linear transformation.